Hello, this is the 3100A high-frequency oscillating ventilator, and my disclaimer is that I'm not doing this for any hospital, any company, any employment purposes. It is strictly for a school project. The high-frequency oscillating ventilator is a mode of ventilation used in many neonatal intensive care units for infants with various respiratory problems. Before we get started, I just want to note that I have already performed a circuit calibration as well as a ventilator performance check on this machine. To turn the machine on, the on-off button is down below here. Simply turn it on, and the machine will power up. In order to start the oscillator, hit Start Stop, and the pre-ordered settings that I have already placed on the machine appear, which are a mean airway pressure of 12.5, an amplitude or delta P of 26, 33% inspiratory time, and a 15.0 hertz. This form of ventilation is unique in the way that it has an active inspiration and an active exhalation. Starting on the far right, you'll see the bias gas flow. This is measured in liters per minute and helps to maintain and set the mean airway pressure. Right to the left of the bias flow is the mean airway pressure control here. This is used to set the tension on the machine's diaphragm, which helps to oscillate the gas flow to the patient. The mean airway pressure monitor is on the far left. It is measured in centimeters of water. This helps to, along with the FiO2, helps to control the patient's oxygenation. If you're changing your patient from conventional ventilation to HFOV, you will need to set your mean airway pressure 2 centimeters of water above the patient's mean airway pressure reading on conventional ventilation. Below the mean airway pressure monitor, you see alarms of this ventilator. See the maximum airway pressure alarm limit and the minimum airway pressure alarm limit. These are set 3 centimeters of water above and below our ordered mean airway pressure of 12.5. I mentioned FiO2. Even though it is not on the face of this ventilator, the FiO2 is controlled by an air oxygen blender seen on the side of the ventilator. Unless you're actively weaning the FiO2 on your patient, you may wish to manipulate the arterial PO2 by increasing or decreasing your patient's mean airway pressure. Ventilation is determined by amplitude or delta P, inspiratory time, percent, or frequency measured in hertz. The amplitude is set by the power control knob, which is right beside it. Amps are determined by the forward and backward excursion distance of the piston, which is directly to the left. The piston control knob is down low on the ventilator, where after you make ventilator changes, it may be necessary for you to recenter your piston. Practitioners observe the amplitude on their patients as having bilateral and equal chest vibration or chest wiggle. To control the carbon dioxide in your patient's blood gases, first try adjusting the amplitude, or delta P. Again, this is regulated by the power setting. If your patient has an increased arterial PCO2, try increasing the amplitude. If the patient has a decreased arterial PCO2, try decreasing the amplitude. The secondary measurement that you may change for an increased arterial PCO2 is a decreased hertz. Please do not make both of these changes at one time. Try adjusting the amplitude first, and if you do not get your desired effect, then try adjusting the hertz. The frequency is measured in hertz, is determined by the number of piston excursions. For the neonatal population, we usually use 12 to 15 hertz on the patients. 1 hertz equals 60 breaths per minute. So if this machine were currently on a patient, a 15 hertz would equal 900 breaths per minute. The percent inspiratory time is very seldom changed. This control helps to control the time for the piston displacement, which in turn also helps to control carbon dioxide elimination. That was a brief overview of the controls of this 3100A ventilator. Thank you so much for viewing.